Okay, so I'm going to continue 1.8, and these are pretty much all 1 over x. And before we continue, we should understand a little bit about the function 1 over x. Okay, it looks like this. So get used to how it looks. The parent function is in quadrant 1 and quadrant 3, and we need to understand why it's that shape and what it's doing. Now, normally, if you look at it, y is going to be the result of 1 over x. And one of the basic rules of math, two basic rules, are you can't square root a negative number, and you cannot have a 0 in the denominator of a fraction. It's an invalid result, so it cannot exist. As a result, this x can never be 0 in this graph or equation. So we have what's called a line called an asymptote, a vertical asymptote, that exists because x cannot be 0 ever. So it never can reach that blue line. And it will try if we look and we go up. It looks like it's touching it, but there's always a bit of a space there. And same with the bottom. There's also a symmetry here through origin that eventually you'll learn is called an odd function when it has this kind of symmetry through origin. In other words, every point on this side, if we draw a straight line through origin, exists on the other side. And this will happen no matter what I do to it. And I'm not going to adjust it yet, but if I put a 3 beside the x, it's going to do that. If I put a 9 up here, right, let's see, 9, it's going to do that. So it doesn't matter, it's always going to have that symmetry through whatever its asymptotes are. Now, where's another asymptote? Well, it turns out another asymptote is y is equal to 0. You're always going to have this y is equal to 0 asymptote when the top numerator has fewer x's than the bottom numerator. And what do I mean by that? And I'm kind of jumping a step here, but if I have x squared down up here and x cubed, which is one more x down at the bottom, I'm going to have a y is equal to 0 asymptote. Get more into that in a second. Let's just go back to 1 over x. But because there's fewer x's in this numerator and an x in this denominator, y is equal to 0 is going to be an asymptote. But also logically, why can't I ever get a result of y of 0? Well, if I can never create a 0 out of this result here, I'm never going to get a y is equal to 0. There's no number I can put in for x that will get me a result of 0. I can put in 0.000001 for x, and y is not going to get anywhere to 0. And I can put in, instead the reverse, I can put in 1,000,000 for x. And look, y is getting close to 0, but never reaches 0. So we can see there's no result I can put in for x that will create a y is equal to 0, which is why you have this horizontal asymptote. Now, word of advice, these asymptotes will move as the graph itself is translated. But I want you to learn a little bit about a fraction first. 1 over 1. It's 1. What happens if I increase this numerator? In other words, I go up from 1. Well, it's obviously that the result also goes up. So as the numerator goes up, the result goes up. Whatever I put in the numerator, the result goes up. What happens when I increase the denominator? Oh, well, the result goes down. The result goes down. It gets smaller. And the more I put in that denominator, the smaller that result gets. So that means when the denominator increases, the result decreases. When the numerator increases, the result increases. Well, right now, I've got a 1 over x situation. I've got a 1 over x situation. So it stands to reason that as x gets really small, so as it approaches 0, y will get really big. And as x approaches really big, and let's say plus 1,000,000, or just plus infinity, y will approach 0, because y is the result that I'm talking about. Well, that explains why, if I were to graph this, okay, and I were to put the asymptote there on the red line, as x approaches the asymptote, which is 0, y gets huge. So I would put a dot there. By the way, what happens when x is 1? When x is 1, 1 over 1, y is 1. So you'll see a point right here at 1, 1. And let's pretend the horizontal asymptote is here, or the x-axis in this case, and continue. And now as x gets huge, approaches infinity, y approaches 0. So I'm going to get close to the x-axis but never touch it, which is why you see this weird uniform kind of lying on its side C. What about the negative values? Well, let's start with the infinity for x. As x approaches negative infinity, which is way over here on this side of the graph, we can see that 1 over negative a million is a really small number, but it's still negative because it's plus 1 divided by a negative number. So you get really close to 0, but negative, which is on this side of the quadrant. So that means I approach a dot like here. What happens when x is negative 1? 1 over negative 1, y is negative 1. So when x is negative 1, y is negative 1. So we'll have a point right here every time. And these are the 2 points you should memorize. 1, comma 1, and negative 1, comma negative 1. Now, finally, what happens when x approaches 0, but from the negative side? In other words, as it gets this side. Well, that means this number gets really small, so the result gets really huge, but because I have a negative number in the denominator and a positive number in the numerator, I approach negative infinity, which is way down here on the y-axis, which explains why I have that shape. Once you understand fractions a little bit, this shape makes perfect sense. As x gets big, y gets small. As x gets small, y gets big. And the negative is just dependent on whether x is negative or not. Because the numerator is positive, the result will always be negative if x is negative, and always be positive if x is positive. It makes perfect sense when you look at it, but let's, pardon me, look at what happens with transformations. Well, anything beside the x is supposed to be a translation opposite 2 to the right. If my asymptotes are at x is equal to 0, and y is equal to 0, and I move my graph from here to here, suddenly this one on the bottom is crossing the x asymptote, which means the asymptote will also move 2 to the right. So the new asymptote should be x is equal to 2. Let's see if that's true. Yep, sure enough, look at this bottom red line. It's crossing the old blue asymptote, and it's now over here. So let's move the blue asymptote at x is equal to 2. Oh, look at that. The asymptote moved as the graph moved. What happens then if I add a 3 to this graph? What happens if instead of 1 over x minus 2, I add a big old 3 over here? And just like all functions, this is now a y transformation. And it should be raising the graph by 3. But if the asymptote is here, the horizontal asymptote, and I raise the graph, it will be cutting through this time. Let's see if that's true. So we're going to get rid of that 2. We're going to get rid of this, put it back at 0. We're going to add 3. Well, sure enough, look, this part of it is cutting through my horizontal asymptote right there. Let's see if the horizontal asymptote moved up by 3 as well. Yeah, it did. And it looks like it's touching, but when you zoom in, there's always a space. So that means the asymptotes move with the translations. So whatever translation to the right your graph has, the asymptote will move over it. But just be careful. The reflections add a whole new dimension to it. So if I have a reflection here, well, I'll put the asymptote back to 0. If I have a reflection here, sorry, it kind of reflects as it should. It looks like it's reflecting as it should through the y-axis. However, both will look like the same reflection. One is actually reflecting through the y-axis, and the other one, this one, is reflecting through the x-axis. It's a y transformation. This is an x transformation. But be careful, because if I have x minus 2 here, I've moved the whole thing to the right. But if I put a minus here, boom, it's all going through the asymptote now. So I'll put the vertical asymptote back. Now watch what happens when I put a minus on the x, which is a y transformation. it's flipping on the asymptote. So just be aware of that. And the same thing will happen. Let's add both of them here, where I also move it up by 3. That looks like a totally normal 1 over x, except it's translated 2 to the right and 3 up. And that means that 1 comma 1 should move to, let's add 2 to x, 3. Let's add 3 to y, 4. So the new 1 comma 1 should be 3 comma 4. Let's see if it is. Try to get right in there. Can't quite get it. We can see it right there. There it is. Which means the negative version, which was negative 1 comma negative 1, if I add 2 to x, becomes 1. And if I add 3 to y, becomes 2. So I should see 1 comma 2 over here. And I do. So the 2 points translated nicely. The asymptotes translated. And this graph is making perfect sense. Just remember that if I put a negative here, it's reflecting in the y-axis, and if I put a negative here, it's reflecting in the next x-axis. But those reflections look identical because this is symmetrical through the origin. That's why. We'll get more on reflections. It doesn't really matter so long as you apply the same rules as you would to any function. So let's look at number 10. Here we go. So we're just going to describe the transformations, and I'll also say what you would do to the points. So we know the main points, as I said, are 1 comma 1 on the parent function, and it's always good to know the parent function points. But if you don't, do your formula, make yourself a T cell with x's and y's, punch in a value of x that's easy to do, determine the y. Punch in a value of x that's easy to do, determine the y. You can even do bigger values. So for instance, when x is 2, y is a half, and when x is negative 2, y is negative a half. When x is a half, or 0.5, let's say a half, oh, there we go, y is 2. And when x is negative a half, y is negative 2. You can do more points. So obviously, these points become harder to plot because they're halves. So that's why we just stick with the 1 comma 1. So there we go. Now let's look at this one. What's going on here? Well, we just did this in Desmos. This will move the entire graph to the right by 2, which means since that's the only transformation, the new asymptote will be at x is equal to 2. The horizontal asymptote will remain at y is equal to 0. Always label your asymptotes. The new points, 1 comma 1, I just add 2 to the x's. So this is called a horizontal translation 2 to the right. So when I add 2 to the x's, I should get 3 comma 1 and 1 comma 1 will be the new. And you'll notice this one translated up to that one, because when I add, oh sorry, it'll be 1 comma negative 1. It'll be down here. 1 comma negative 1 because the y doesn't change. So if I do this over here, get rid of that, and forget the y is equal to 3, it's back down to 0. Let's see if those points did indeed translate to where I thought. So there's 3 comma 1, and there's 1 comma negative 1 right there. I can't quite get in there, but it's there. Positive 1, negative 1. So you can see this follows the same rules of transformations as everything. What about this one? Well, this one has no x transformations. It just has a y transformation. And the y transformation is vertical translation up by 2. So that means you take all your y values and you just add 2 to them. And you take your y horizontal asymptote and you add 2 to it, and the vertical asymptote will stay the same. So that'll be the main points. And you can always prove this by first putting in your asymptotes. Are we adding 2 or 3? I can't remember. 2. And then putting in a point that you think will exist and label it. And put another point that you think will exist and label it. And then put in your graph and see if you nailed it. Oops. So what did I do wrong? Oh, this should be negative 1. There we go. And there's a good example if you catch yourself making a mistake. But you can see the translated points are there. There's the new horizontal asymptote, and the vertical asymptote has stayed the same. So it translates exactly as expected. What happens with this one? Well, notice the numbers outside of the x. It's nowhere near the x. So this is a y transformation, which means this is called a vertical compression by a factor of 1/2 or 0.5, which means I multiply all my y values by half, which means my new points will be 1, 0.5 and -1, -0.5. So I'll just put half there, put half there. There's been no change in the asymptote, so I'll put the asymptotes back because there's no vertical translation up or horizontal translation. And look at that, I forgot to put the negative here. So there's a repeating error. Notice the stretches. Oh, I didn't quite get it right. So -0.5, -0.5. Let's make sure I got that. -1. Yeah, so notice the stretches. You would think, oh, shouldn't it appear here? But no, the stretch kept the x value the same, right, at -1. So normally it was down here, but the y value has been stretched over there. So you might see this doesn't seem symmetrical. However, if I connect those 2 points, they reflect perfectly through the origin. So you can also see it if you go back and forth, right? Here's the normal one. And here's the compression, not a stretch, compression. Okay, so it follows the same rules. What's going on with this one? Well, this one's harder to see because of how they've written it. But really what's going on is you might be tempted to say, oh, this is related to the x because it's over the x. But it's not really. It's the same as this, and this is how they should have written it. It's just the expanded version of that. And I'll just put the bracket over here. Do like that, and get rid of this, and get rid of that. And put the line over it like this. And then I'll even stretch my bracket so it makes more sense. There we go, something like that. Anyway, this makes more sense when you can see it like that, because obviously the 2 multiplies in and becomes a 2. And so it's very tempting to see this as an x transformation. And there actually is a version of the x transformation that is occurring, and we'll get into it in a second. But I would describe this as a y stretch by a factor of 2. So multiply all your y's by 2. And you get 1, 2, and -1, -2. And that will do it. Now, technically, really technically, and I don't want to get too confusing, if I have it 1 over x, and I take the x down here, and I multiply it by a half, it becomes x over 2. And then if I do this, 1 over 1 divided by this fraction, it also becomes 1 over times 2 over x. So technically, I could also, and this is a very annoying, and you should skip it if this confuses you, I can also describe this vertical stretch as a horizontal stretch by a factor of 2. And this is obviously an easier way to look at it, and I prefer you look at it this way. But technically, you will also have this. This is also possible. So if I'll just show you both, and I'm going to label the new one just so we can see it. Okay. And up here, I'm going to start putting I'll do it. So 2 over x, right? We can see that's the translation. Now I'm going to rewrite it as a y transformation, and you're going to see it's the same. Same thing, green and blue line are the same. Now I'm going to even write it as a very bizarre X transformation. And look at that. Purple, green, and blue are the same. But obviously, I prefer to just think of it as this way. But because there's a one-to-one relationship between X and Y, in other words, X isn't being squared or anything, you can see that you can make X transformations look very much like Y transformations and vice versa. For squares, it's slightly different. For instance, and I'm just going to backtrack, this is an X transformation on a parabola where I multiply all my X values by a third. However, this graph, think about squaring the top number, you would get 9x squared, is a Y transformation where I multiply all my Y values by 9. So here's an X transformation where I multiply all my X values by 1 over 3. And here's a Y transformation where I multiply all my Y values by 9. But they're the same graph and pretty much the same transformation. And it makes sense when you square everything in this bracket, it becomes that. For 1 over X, because there's no square, it's a direct relationship. I hope that sort of made sense. But my point is you can create equivalent X and Y transformations that produce the same graph. This is simpler to do. All right, let's move on. And finally, the last one. That was that one there. This one's similar, right? But this one's very obvious that it's associated with the X. Right? So this one's right beside the X, so I can rewrite that as an X transformation. And it's not a stretch, it's a compression by a factor of a half, because that 2 is right by the X. You'd be tempted to think of it as a half because of the 1 up top. But you've got to remember that you've always got to compare it to the parent function, which is right over here. And what has changed? All that's changed is that there's a 2 beside the X. Therefore, the 2 is affecting the X, not the 1 over 2. And that means it's a compression by a factor of 2, which means multiply all your X values by a half. So I'm going to get 0.5 comma 1 and negative 0.5 comma 1 comma negative 1. Make that mistake over and over again. So there's the points I would expect, and now let's get rid of this 2 and put the 2 beside the X. And turn it on. There we go. The asymptotes weren't affected because there's no translation. Just those points were translated. Now I also want you to take note that this, which is a X compression by a factor of 2, can also be rewritten as this. Which is now written as a Y transformation or Y compression by a half. So now we'd multiply all my Y values by a half, and guess what? I'm going to get the same values, and it's going to look exactly like the same graph. I can even find these points on this graph. There's that one. And there's that one. It's just a different written transformation. So I'm going to turn off this graph, and I'm going to show you how I write that one. And don't bother, I just want you to understand that there's a connection here. See, the purple graph and the green graph are the same, even though this is written as a X transformation and this is written as a Y transformation. It sort of produces a similar graph but different transformations. You'd be tempted to say it's the same transformation. It's the same result, but this is written as a Y transformation. This is clearly written as an X transformation. Nitpicky, I know, and maybe confusing. If it really confuses you, skip that part of it. I'm just trying to show you there's always an interconnection between y and x because of this equal sign. Y is always dependent on x. And finally, this last one, this minus sign, and here's another prime example, is written outside the fraction, so we can consider it a y transformation, so it's a reflection in the x-axis. But I want you to notice that even when it's a reflection in a y-axis, even when it's a reflection on the y-axis, it'll look the same. Here's a reflection in the x-axis, which means I have to multiply all my y values by -1. Okay? But now I want to show you a reflection in the x-axis. I'm going to go back to the original values here and show you that it can look just the same. Now I just have to multiply all my x values by -1. And look at that, the same points. Really confusing because of the same points I've written in, just the translations are technically different, even though it produces the exact same graph. Just going to change this to blue as well. There we go. So again, skip this double translations I'm describing if it's confusing to you. How it's written is how you should describe the translations. And then they get you to keep doing this for these. And it's just important. Here's the trickery that teachers love to do. This part here is not an accurate translation. Do you see an x plus something with a 3 or whatever in front? No, you don't. You see one big bracket, which means that's not a correctly expressed transformation. It's actually this. Suddenly that what appeared to be a 6 translation to the left is actually a 3 translation to the left. And you'll be able to see this if you write it into the Desmos exactly like that. You'll see that it's actually a 3 transformation to the left. And notice that the compression of 1/2 is still the same. It's just the teachers love to do that so you get this part wrong. Be warned. Notice that they're each like that. Okay? So this one's specifically talking about a parabola, 11. I'll just bring the other ones down. And a parabola's main points are -2, 4, -1, 1, 0, 0, 1, 1, and 1, 4. So this is only an x transformation. Everything's going on around the x, which means I have to describe it. It's a compression. It's a horizontal compression by a factor of 1/2, which means multiply your x values by 0.5 or 1/2 or divide by 2, whatever you want to describe it. I prefer this description. And then that +3 is a horizontal translation, 3 to the left. So subtract 3 from all x values. So that means I'm going to just be solely working with these x values. I'm going to separate the y values. They don't change. And then I'm going to put them through the ringer. Each time they're going to be multiplied by 0.5. And then subtract 3. So I'm going to do that, the 0.5 first. What's -2 by 0.5? It's -1. Then when I subtract 3, it becomes -4. What's -1 when I multiply by 0.5? It's -0.5. When I subtract 4, subtract 3, it becomes -3.5. What's 0 multiplied by 0 by whatever? It's 0. And that becomes, when I subtract 3, -3. What's this when I multiply by 0.5? It becomes that. And then that becomes, when I subtract 3, negative 2.5. What's this when I multiply by, oh, that should be a 2, sorry. That's the next point, 2. When I multiply this by 0.5, I get 1, and when I subtract 3 from it, I get minus 2. Which means that these are my new points with these. And if I'm going to graph it, right, you'll want to take your graph paper. Do I have one? No. There we go. You want to make your units 1. And you want to just get a nice big slice of it. Try to fold that up. There we go. Take a picture. Put it wherever you want. Put it down here. Take your points. Don't forget we're going to label our points. And we'll just make it a little bit better. A little bit tighter. And you should put a comma between each of them. And we're just going to label them. By the way, did our asymptote change? Yes, our vertical asymptote should have moved 3 to the left, like that. So that's what I'm going to start with. I'm going to draw a vertical asymptote right there. And I'll always label it like this. But our horizontal asymptote did not change. Let's keep it red as well, because there was no horizontal translation. So I'm going to label it as y is equal, and you can even say horizontal asymptote, y is equal to 0. And vertical asymptote, like that. Then you just plot your points. Minus 4, comma 4 is up there. Minus 3.5, comma 1. Right there. Oh, sorry. This is a parabola. My bad. There's not going to be any asymptotes. I forgot we're dealing with a parabola. Minus 4, comma 4 right there. Minus 3.5, comma 1 right there. And remember that this next point should be the vertex, minus 3, comma 0. Then I'm pretty much going to see a reflection. So here's the line of symmetry for this. And you can even label that one instead of an asymptote. You just call it line of symmetry. And then the other points will be reflected exactly on the other side of that. Minus 2.5, comma 1 and minus 2, comma 4. And you don't even need that many points. You can just work with 2 points. It all depends on your teacher. And I'll try to get symmetrical. There we go. Pull her down there. Do that. Squish it a bit. There we go. Not quite, but good enough. So what happened to this parabola? Notice that it's thinner. That's because it was horizontally compressed by half. In other words, it got 2 times thinner. And then it was moved, translated horizontally, 3 to the left. And it's quite obvious. We can see the 3 to the left. The asymptote moved with it. And we can see this is a thinner parabola. Let's confirm this by putting both formulas into this to show that it's deceptive. So 2x plus 6 was how they wrote it. And now I'm going to write it the way it should be written. Turn it off and on. Oh, look at that. They're the same thing. Let's focus on the red one. The red one looks like it should have been 6 to the left, right? But we can see that it's actually 3 to the left. Doesn't matter how you write it, by the way. I can use the function notation like this. use the function notation like this. It's essentially saying take this function and translate it like this. Notice I've done it correctly here, and that the green and the purple graphs are the same graph. This is just the correctly expressed, and this is what your teacher likes to throw at you to trick you, and this is the original. You can see it's thinner, and it's moved to the left by 3. They're all pretty much the same thing. They're all trickery. This is a square root function. What are the normal points of a square root function? 0, 0, 1, 1, 4, 2, 9, 3. It looks like this, and it's above the x-axis and to the right of the y-axis, and only has a domain arranged that way. Okay, what's this translation? There's a reflection in the y-axis, so that means we're going to be going that way. But you'd be tempted to say it's 12 to the right. Same rule. That's not correctly translated. It's actually this. So you at first thought it was translated 12 to the right. It's actually being translated 4 to the left, which means I have to multiply all my x values by -1/3, or divide them all by -3, and then subtract 4. So when I do that, so multiply first and then subtraction. So 0, nothing happens to it, but when I subtract 4, that's what happens to it. And then 1 becomes divided by -1/3, so it becomes, or sorry, -3 becomes -1/3, and when I subtract 4 from it, becomes this, essentially. Nothing happens to the y's. 4, when I divide it by -3, becomes -1 1/3. When I subtract 4 from it, becomes this. And the last one, when I divide it by -3, becomes -3, and when I subtract 4 from it, it becomes -7. So we should see these points. Let's see if I still have my... I should have kept a copy of that. Okay. I'm not going to graph all these because there's no point in doing that. Okay, that's good. I'm just going to take these points down and show you how the translation worked. So I thought it was going 12 to the right. It's going 4 to the left. And it's reflected. So normally it's going that way. Now it's going to go that way. This is going to be, oh, those aren't the right things. It's these ones. Notice that this is going to be the new vertex because everything moved to the left by 4. So it's going to start here. Then it's barely going to move over and go up to here. Then it's going to move over essentially 1 and go up to there. This is the only one that's pretty clean right here. Boom. So what did the third do? It essentially squished, well, the 3, it was actually written as 3x, essentially squished the shape by a factor of 1/3, compressed it by a factor of 1/3, squished it to 1/3 the size. Sort of like that. Not quite like that. Just a little bit off, but anyway, good enough. And notice it's now going this way. This is the vertex, which came about from the first point. And its range is still the same, but its domain has changed to x is smaller or equal to -4. So that was huge. We thought it was going to go 12 over here and then go this way. But it's clear it's very deceptive when it's written improperly. Let's see if that's true. Here's the parent function. Here's the translation as written. There's -3, sorry. There we go. Looks like it should move 12 to the right. But sure enough, look at that. It moved 4 to the left. Here's how it's written properly. Same graph as blue and red are same graph. That multiple dot thing just means they're sharing all those dots. Same graph. Here's how it would be written as a formula. Notice that Desmos is capable of drawing them all, no matter which one I use. This is the incorrectly expressed one. This is the correctly expressed one, taking this function and transforming it. And this is just the actual equation rewritten. All important to sort of connect and understand. This last one that they do is the same thing. I don't think I'm going to sketch it because, you know, how many times do you want me to resketch something, especially when we have Desmos to prove the point. Just know that we're working with the parent graph, and the parent graph is plenty if you know the parent graph. Anyway, I ended up screwing the sketch anyway, so let's do this last one. This last one's this. And we're working clearly with an absolute function. And it's incorrectly expressed over here. Fortunately, there's no you can see how translations can really get. But I have to factor a 4 out of it. So really what's going on here, it's a compression horizontally by a factor of a quarter and a horizontal translation 2 to the left. So that means multiply, or if you want, divide all x by 4 and subtract 2. And since we're working with an absolute function, the points of an absolute function are actually very easy. The numbers will match, but the signs will change. On the right, it's 2, 2, 1, 1, and 0, 0. And on the left, it's minus 1, 1, minus 2, 2. And it goes on. And all y values are positive. There's no translations, so it's still going to be that. There's no vertical or horizontal reflections, rather. And so that means I divide all these by 4 and add 2. So I'm going to just do it very quickly. So I get a half, so 2.5 comma 2, a quarter, or 0.25 comma 1. Oh, then I have to subtract 2. So negative 1.75. And this one, sorry, should have been added, should have been subtracted 2. So this is 1, and subtract 2 is minus 1. 0, and then subtract 2, comma 0. Notice the y values don't change. This one, negative quarter, so negative 2.5 minus 2, negative 0.25 minus 2 is this. And then this one, a negative 1, and then subtract 2, negative 3, comma 2. Now if I take that and I plot it up here, just point by point like that, I should be able to nail this. So I got negative 1, comma 2, label it. Negative 1.25, comma 1, label it. Negative 2, comma 0, label it. Negative 2.25, comma, it looks like 1, label it. And negative 3, comma 2. Now, unfortunately, I have to stop at this because I'm getting a call coming in. And I hate doing it in 3 parts, but I'll just zoom in. Actually, I'll unlabel it so we can just see the points. And you should see a big V structure. Oh, I did one of them wrong. Looks like that one. The vertex I did wrong. Let's see. So, divide by 4, subtract 2. Got it right. Divide by 4, 0.25. Subtract 2. Got it right. Divide by 4. Oh, this one's not. That's divide by 4 is 0.5 and subtract 2. So that should be that one. Divide by half. 4 is a quarter. Yeah, this should be negative 0.7. So I did a lot of arithmetic errors. Divide by 4 is a quarter, and then subtract 2. This should be -1. I did a ton of arithmetic errors, sorry. I was dividing by 2 instead of 4. So redoing that. Actually I did this wrong too. So divide by 4 is a half, and then subtract 2 is -5, 1.5. There we go. That should do it. Let's see if I can correct these. Looks like the vertex is the only one I got right. That one I'll have to check again. So it's -1/4 minus 2. No, I got that one right. This one I got wrong. So just butchered it. Now you can see a V shape, and you could even conceivably draw it. But I'm going to do just the formula. Up top or down below. Oh, I don't know why it's doing that. There we go. F of x is equal to the absolute value of x. So there's the normal one, and here's the g of x when I take f, and then I multiply it all, I think, by 4, and then I think I'm shifting it to, correct? Like that. There, I nailed all the translated points after correcting them. But here's also g of x with the improperly expressed one. If I turn it off, you can see I get the same graph. So learn, your teacher loves this, learn that the x values can sometimes be expressed incorrectly, and it'll make you graph it absolutely incorrectly. I have to run, which is unfortunate because that's only number 10, but so be it. I'll do the rest in another session.